Hello everyone, today we're going to talk about the X-ray imaging system. We're going to talk about the generalities of the system itself, the operating console, the autotransformer, and the MA selector. Diagnostic imaging systems, they all operate at voltages between 25 to 150 kVp and at tube currents of 100 to 1200 mA. Those are very important facts for you to memorize, especially when you're going to be studying for the registry. So 12 to 150 kVp, 100 to 1200 mA. Fluoroscopic units generally have their X-ray tubes under the examination table. We can also call the examination table the couch, and this table, as you know, may either be flat or it could be curved. It must be uniform in thickness, as transparent as possible to X-rays, and the material of choice today is carbon fiber. Carbon fiber, it's lightweight, but it's very strong. And most of the tables today are floating. They're easily locked or unlocked. The fluoroscopic table or couches are identified by their degrees of tilt. For example, we could have a 30-90 table. What that means is that the table would tilt downwards 30 degrees in the Trendelenburg position, come up to a full upright vertical position, which would be your 90 degrees. Every X-ray imaging system has three parts. We have the X-ray tube, the operating console, which is where you stand. It allows the technologist to control technical factors, and the high voltage generator, which could be housed in an equipment cabinet against a wall or in a drop ceiling. Most of the time today, because we use high frequency circuitry, it's a lot smaller, takes up less space. We can put it up into the drop ceiling, gives you more room in the X-ray room itself. As far as the operating console, radiation quantity is the number of X-rays in the beam. It's either expressed in milligray or in milligray per mass. Radiation quality is the energy of the X-ray beam. It's expressed in kVp or in half-value layer HVL. And the console, where you stand at, provides for control of what's called line voltage compensation, which we're going to talk about today, kVp, MA, and exposure time. All circuits that connect the meters on the control console are at low voltage to minimize the possibility of electrical shock. Now, this is going to be important for you to remember that everything on your control console has to be at low voltage. When we begin looking, as we are today, at the Xray circuit, we're going to notice that there's a high voltage portion and a low voltage portion. Most control consoles today are digital or touch screens, which allow the technologist to easily select the correct technical factors. In fact, most of your equipment today, you're going to do a hand, an abdomen, whatever. You simply click on it and it sets all of the technical factors up for you. Now I want you to look to the drawing at the right. This is a part of the X-ray circuit. I want you to notice on the left-hand side where it says line monitor, it looks like a plug is coming in. This is representing the incoming power source that we're going to get from the electric company. Now, the first thing that electricity is going to go into, as far as the circuit is concerned, is called an autotransformer. I'd like you to look down at the bottom of that autotransformer and notice it says line compensator. Sometimes it's called a line voltage compensator. Here it says line compensator, switch, and meter. What's important is that most systems today are designed to operate on 220 volts of power. So we have power being generated, 110 volts, 60 cycles by the power company. Of course, if we take two 110 lines, we end up getting our 220 volts of power. And that's the amount of power that's going to be fed into the circuitry itself. It's important to understand that from the power company, we are getting volts, but to take an X-ray, we need kilovoltage, thousands of volts. So there's going to be things within the circuit that are going to be able to take that voltage from 220 and bring it up to the level that you're going to need to take an X-ray. For example, you're taking a chest X-ray, you might need 120 kVp. If we think about it, that's 120,000 volts of electricity that we're going to need. Now, unfortunately, the power companies cannot deliver exactly 220 volts consistently. Okay, sometimes it goes up to 225, sometimes down to 215. Now, most of the appliances in your home, it doesn't matter really that much if we up the voltage or bring the voltage down a little bit, as long as we're around that 220 volts. However, for the X-ray circuit, 220, it needs to be very, very specific. Because what's going to happen is the voltage coming from the power company is eventually going to be fed into what we call the step-up transformer, which is going to bring you to your kilovoltage level. Now, there's a formula that we had learned about transformers, and we know that when we take the voltage on the secondary side, we compare it to the voltage on the primary side. If it's a step up, the voltage on the secondary side is going to be increased, and it's going to be increased to a certain number. The step-up transformer has a fixed number of coils. That's important to remember. The step-up transformer has a fixed number of coils. So in order to vary the amount of electricity coming into the step-up transformer, we have to somehow manipulate that voltage of 220 up or down before it gets fed into the step-up transformer. Now, the 220 volts coming in to the equipment itself, into the circuit from the power company, can have a variation by as much as 5%. Once again, we want to be very specific and have exactly that 220 volts. If you didn't get it to exactly 220 volts and you had this variance, and then you fed that amount of electricity into the step-up transformer, which has a fixed number of coils, you'd get very inconsistent X-ray production, and this would certainly then affect the image quality. So down at the bottom on this drawing to the right at the top, you have the line compensator. What this does, remember, is you have that variance of the 220 volts coming from the power company. Maybe it's 225. Okay, we got to get it right back to 220. And that's the job of the line compensator. It adjusts the incoming voltage to exactly 220 volts. Now, on older equipment, you actually had a dial on the control panel, which you had to literally adjust manually. It was almost, it appeared as a needle, basically, and there was a line right in the middle, and there was an arrow, and sometimes the arrow would be to the right or to the left of the middle line. So what you had to do as a technologist is when you came into the room, before you made the exposure, you'd have to turn a dial, and when you did, that little needle, that little arrow would jump, and you would keep turning it until you got that needle right in the middle, right where the middle line was, and that would tell you then that you have now 220 volts. We don't have that anymore on the control panel. It's all done internally. Okay, so the line compensator is still there. It's not like it's gone away, but it's nothing that you, the technologist, will have to manually adjust anymore. It's all done internally by the circuitry itself. The power supplied to the X-ray imaging circuit is delivered first to the autotransformer. Now, when we Think about transformers. We studied them a little bit before. Most of your transformers have at least two coils. However, the autotransformer only has a single coil. This is why we have that prefix auto. Auto means self. The autotransformer only has a single coil. This single winding is designed to supply a precise voltage to both the filament circuit and to the high voltage circuit. So as we continue our study of the circuit, what we're going to see is that one part of the circuit is going to be the high voltage part of the circuit. That's the part of the circuit that's going to have a step-up transformer. Because when we say step up, what are we stepping up? We're stepping up the voltage. In the other part of the circuit, we need low voltage, and we need low voltage to heat up the filament. To heat up the filament, we need low voltage, high amperage. So in the filament part of the circuit, this is going to be the low voltage part of the circuit. We're going to need a step-down transformer to take that voltage of 220 and bring it way down. Now, of course, when we bring the voltage down, the amperage goes up. So the autotransformer is responsible for supplying voltage into both parts of the circuit. Over on the drawing on the left, I tried to draw here for you an autotransformer. I'd like you to notice that where it says 220 volts, there's a little symbol which indicates this is alternating current. What I'd like you to notice is that you've got a single coil. What I've done is I've drawn a red dash line down the middle of that coil. You can look at this coil then as having, even though it's just one coil, a primary side, which is on one side of the dashes there in red, and then one side would be considered the secondary side. The next thing I want you to notice is that I've got a connecting wire at where it says number 1 in green. All right, so if we then count the number of coils, starting from that connecting wire, we've got 1, 2, 3, 4, about 5 turns of the coil on the primary side. On the secondary side, we've got 2 arrows drawn. Now these 2 arrows are points of contact. We can also call them taps, T-A-P-S. They're points of contact. And these points of contact are going to then connect to the rest of the circuitry, the rest of the electricity that's going to be going into eventually the step-up transformer. This arrow, this point of contact, has the ability to move up or to move down. So I have one thicker arrow drawn in position number 1, and then another arrow, a little thinner arrow drawn at position which would be 6 here. Now that arrow, that point of contact, moves up and down, and it moves up and down when you change your kilovoltage. Now in older equipment, you don't find this really today much, but in older equipment, when you would turn a dial and you would go from one kilovoltage to another, it would make a very unique sound. It kind of sounded like this. Zzz, zzz. And basically what that was is the point of contact either moving up or down on the autotransformer. If we look at this autotransformer, let's look at the thick arrow. Okay? And remember, I'm looking at the one coil and I'm looking on the right-hand side. So when we have the thicker arrow, position number 1, I've got 1, 2, 3, 4, 5, 6, 7 coils tapped off. Now, if I look on the other side of the coil, the primary side, I only have 5 coils tapped off. So when I look at this, 5 coils on the primary, 7 coils on the secondary, what's going to happen now is I'm going to step up the voltage. I'm going to be utilizing all of the coils on that side. 1, 2, 3, 4, 5, 6, 7. So it's 5 to 7. I'm going to step up the voltage. If we look at the thinner arrow, well, now on that secondary side, I've only tapped off 2 coils. This would be 6 and 7. So now I've got 5 coils on the left-hand side, the primary, but now only 2 coils I'm tapping off on the secondary. So what am I going to do? I'm going to bring the voltage down. So in position 1, where I've used all of the coils on that side, I'm bringing the voltage up. When I bring it all the way down and I'm only tapping off 2 coils on the secondary side, well, now I'm going to bring the voltage down. Now I've only got 7 coils drawn here. Of course, in actuality, there's hundreds of turns, if not thousands, turns on this auto transformer of the coil. Okay, but here I just wanted to do simplistically to show you. When you tap off more on the secondary side, you're going to step up the voltage. When you tap off less on the secondary side, you're going to step down the voltage. So as I said, think of one side of the coil as being the primary side, the other side of the coil as the secondary side. Notice the attachment of the wire on the primary side, approximately 5 turns, which are fixed. The arrows on the secondary side represent a movable point of attachment. If it's in the blue position, there are more turns on the secondary than on the primary side. So 7 compared to the primary having 5. As I said, this would act as a step-up transformer, increasing the voltage slightly. And if it's in the black position down at the bottom, there are less turns on the secondary, only 2 turns now, tapped off. But 5 still remain on the primary side. This acts as a step-down transformer, decreasing the voltage slightly. So I hope that makes sense. Remember, on the secondary side, a movable point of contact, either allowing you to tap off more or less coils. The primary side is going to have a fixed number. This is going to allow you to change that incoming voltage. The Autotransformer Law, it's the same as the transformer law that we've learned before. So you could calculate the voltage on the primary side of the autotransformer, calculate the voltage on the secondary side of the autotransformer. Remember, the formula is secondary voltage divided by primary voltage equals number of primary side windings divided by number of secondary side windings. So on the registry, on an exam, you may get an example like this. If the auto transformer is supplied with 220 volts to the primary connection, which includes 800 windings, what is the secondary voltage if the secondary connection has moved and there are now 1,200 windings on the secondary side? So you think to yourself before you even do any math, and this is what I always tell students, okay, think to yourself, am I doing the math involving a step-up transformer? Well, if I am, my answer in voltage better be going up. If it's a step-down transformer, my answer should be less. So as it says here, think to yourself, there are now more windings on the secondary side, so it will act to step up the voltage. So when we do the math, it would be X number of volts divided by the 220 volts, which is on the primary side, equaling 1200 divided by 800. We're going to cross multiply to calculate for our answer. So we're going to end up with 264,000 equaling 800x. Our answer then would be 330 volts. So we've gone from now 220 and we've stepped it up to 330 volts. This now is the number of volts that is going to be fed into the step-up transformer. That 330 volts is going to be on the primary side. Depending on the number of coils on the step-up transformer, we're going to bring up the voltage from that point. So the purpose of the autotransformer is to allow for adjustments in the kVp that will be used. I want you to look at the drawing. So we've covered so far the incoming power source, which is at the far left. It's not identified, but this would be there. It looks almost like a plug coming in, indicating this is the incoming power source. We said that we need to get it exactly to 220 volts before we do anything. So that's the job of the line compensator or line voltage compensator. You can see you've got the autotransformer. Remember, the autotransformer is going to take now the 220 volts that we're getting from the power company, and it's going to bring it up, we're going to bring it down, and then we're going to feed the electricity. If you follow over to the right, on the top, eventually it's going to get, and I've labeled it here for you, the step-up transformer. Remember, the step-up transformer is a fixed number of coils. So you have to vary the voltage before it gets into the step-up transformer. If you didn't, all you could ever get, if you were only feeding a single voltage at one level into the step-up transformer, you would only be able to get 1 kilovoltage setting. And of course, that would not be practical in radiography. Some of our kilovoltages we need to be high, some of our kilovoltages to be low. So we have to get that number of 220, and we got to bring it up or down before it gets into the step-up transformer. So it says, notice that the electricity will eventually flow into the step-up transformer. The step-up transformer has a fixed number of primary coils and a fixed number of secondary coils that will step up the voltage to kilovoltage to eventually flow through the X-ray tube. So if you kind of follow through on the drawing of the circuit there, you're going to see that eventually that kilovoltage now that is created in the step-up transformer is going to be fed into the X-ray tube, which is at the far right. As I mentioned, to vary the eventual kilovoltage flowing in the tube, the incoming electrical voltage to the primary coil of the step-up transformer has to be varied. Supplying that increased or decreased voltage to the step-up transformer is the job of the autotransformer. Some older X-ray consoles allow the technologist to vary the kilovoltages by tens and ones. So for example, on an older piece of equipment, if you're going to set up 86 kVp, you would have to select 80 and then you'd have to select 6. It would be 2 different dials. And the reason for this is that if we look at the drawing, you can see that you've got major kVp and minor kVp selectors. Your major kVp selector is going to be selecting in increments of 10. Your minor kVp selector is going to be in increments of 1. So on an older piece of equipment, you'd have to set up 80. That's going to be the major taps on the autotransformer, and then 6, which would be your minor taps on the autotransformer. Notice the adjustment in the connections on the secondary side of the autotransformer in the diagram above. So you've got major kVp, minor kVp selector taps. Now when we look at the drawing, so let's go back. What do we have first? We've got the incoming power source. Of course, we've got to adjust it, so that's going to be our line compensator. And then that 220 volts now that we have precisely at that level, we've got to bring it up or bring it down. And that's the job of the autotransformer. Now, what did we say? We said that everything on your control panel has to be at low voltage. There is a kVp meter on your control panel. You know what kilovoltage you are setting. I want you to look at the position of the kVp meter. The kVp meter is going to be between the autotransformer, which is low voltage, and the step-up transformer. Now, what's the job of the step-up transformer? It's going to bring it from voltage to kilovoltage, so that's high voltage. Since the kVp monitor or meter is on the control panel, it must be placed in the circuit in the low voltage section. So we connect it in parallel across, we're bridging it across the circuit between the auto transformer and the step-up transformer. What's interesting is that it's in the low voltage portion of the circuit, and it has to be because it's on the control panel, but it's actually going to measure the kVp. Now, how can it measure the kVp if it's a meter that's only measuring voltage? Well, the computer uses the transformer law, and it knows how much voltage is going to be going into the step-up transformer, which has a fixed number of coils. So whatever that voltage that's going to be going in is at, and then you do the math, you're going to know what kilovoltage you're eventually going to end up with. So if we read the kVp meter is placed across the output terminals of the autotransformer, therefore it is measuring voltage. The electricity has not yet flowed into the step-up transformer for conversion from voltage to kilovoltage. So that's often a question that you see on tests or on the registry. It's a little bit tricky. You would think that the kilovoltage meter, the kVp meter, is measuring kilovoltage, but it's not. It's measuring voltage. So as I said, because this meter is on the control panel, it must be low voltage to prevent death from shock if there is a short in the circuit. You don't want to be touching the control panel and there's a short and now you're touching high voltage. The scale of the meter reads kilovoltage. However, because the varying voltage will flow into the step-up transformer, it's got a fixed number of coils. It's going to be able to calculate then the number of kilovoltage. So the scale of the meter reads kilovoltage, however, because varying voltage will flow into the step-up transformer that has a fixed number of coils. By applying the transformer law math, the meter will be able to report the kilovoltage that will eventually flow in the tube, even though it is only actually measuring voltage at that point. Most operating consoles report the kilovoltage even though no exposure is being made, and there is a device called a pre-reading kVp meter that's incorporated into the circuit. You know what the kilovoltage is when you go into the room. You can see it. Okay, it's there. It's set. The X-ray circuit is divided into two main parts. As I said, you've got the high voltage section. This is going to be used to generate the tube current, that amount of electricity, those electrons flowing from a cathode over to the anode. To do that, we're going to need kilovoltage. We're going to need a step-up transformer. And then, as I mentioned, we have a low voltage section. This is the filament part of the circuit. To heat up the filament, we need low voltage to create thermionic emission. We only need about 10 to 12 volts. So think about it. You had 220 volts coming in. We got to bring down that voltage to 10 to 12 volts. But remember, when you bring down the voltage, you bring up the amperage. So to heat up the filament to thermionic emission, it needs low voltage, only about 10 to 12 volts, but you need really high amperage. Now, I know the numbers 5 to 8 don't sound large, but 1 amp is a lot of electrons, okay, flowing through a circuit. So 5 to 8 amps, you've got a lot of current, a lot of electrons flowing. In the high voltage circuit, the autotransformer is responsible for the kVp adjustment. And in the low voltage circuit, the filament circuit, there is another device that's going to allow you to change your MA values. That's called the rheostat or the MA selector. Basically, what the rheostat or the MA selector is it's a variable resistor. You can either put more or less resistance on that electricity. That's eventually going to change the temperature of the filament, which of course the filament is responsible for doing what? For boiling off electrons. The hotter the filament is, the more electrons are going to be boiled off. The cooler the temperature of the filament is, the less electrons are going to be boiled off. So, what do we do when we take an X-ray? We adjust the kilovoltage. Now we know that that's really going to be part of the job of the autotransformer. And we're going to adjust the MA values. This is the job of the rheostat or the MA selector. As I mentioned, hotter filament, more electrons are boiled off, greater thermionic emission. Cooler filament, less electrons are boiled off. So where is this MA selector or rheostat? So in our drawing, which this drawing is complimentary of Bouchon, it's in your book, when we look at the top part of the circuit, okay, so we've got the incoming power source on the left, the autotransformer. We know where the step-up transformer is, and we've learned that there's a kVp meter between the autotransformer and the step-up. If we look to the bottom part of the circuit, here it's identified, I've drawn it with an arrow to show you, this is the MA selector or rheostat. This is what is going to allow for changes in MA. So when you go from 100 to 300 to 1200 MA, this is the device that's going to be allowing for that selection to be made. That's the amount of electricity now that's going to be fed into the step-down transformer, which also has a fixed number of coils. So it says the MA selector rheostat is a variable resistor. It adjusts the voltage or amperage, voltage and amperage, that will enter into the step-down transformer. Making MA adjustments on your control console changes the resistance of the electric flow through the filament part of the circuit, thus bringing the filament to a higher or to a lower temperature. The X-ray tube current is monitored, just like your kVp was monitored, with what's called an MA meter. Now, where is the MA meter? This is interesting because the MA selector is in the filament part of the circuit, but the MA meter is actually, look at the drawing here, connected to the middle of the secondary winding of the step-up transformer. Why is it there? Well, this is a meter that is on your control panel, but it has to measure the amount of electrons that are eventually going to flow across the gap between the cathode or the anode. We've got to make sure, because that meter is on the control console, that it is low voltage. But you're saying, well, wait a minute, it's in the high voltage section. But the position of where it is connected becomes very significant. If we read what it says here, because the meter is on the control panel, it must be at low voltage, yet it must measure tube current, the number of electrons flowing from the cathode to the anode. Therefore, the meter is placed at the middle of the secondary winding of the step-up transformer. in this location, and only at that location on that coil, the voltage is always 0 due to the alternating current flowing through the coil. And we'll get more into that when we talk about the step-up transformer. But in that position right now, I just need you to know the MA meter is located at the middle of the secondary winding of the step-up transformer. That terminology must be memorized. That often is a question on the registry in the physics portion. They'll ask, where is the MA meter located? The MA meter is located, once again, at the middle of the secondary winding of the step-up transformer.